Okay, in this lesson we're going to be looking at some different applications of logarithms, and in particular using logarithms to solve word problems involving exponential growth and decay. You should be by now familiar with both exponential growth and decay, but what's going to be new in this course is the ability to solve for the exponent in exponential growth and decay questions, so the number of time periods in other words, without using trial and error. So prior to this, you would have only been able to use trial and error to solve these types of questions. But in this lesson, the first part should look very familiar. I've given you the formula for exponential growth and decay. And just to jog your memory, the formula would be y equals a times b to the x. And here we've listed what all those variables represent. So y would be the amount you end up with. A would be your initial amount. B is either your growth or decay factor. So when dealing with exponential growth, B would be equal to 1 plus the growth rate. And when dealing with exponential decay, B would be equal to 1 minus the decay rate. And X is the number of time periods. So for example, this first one says, the first artificial satellites were put in orbit in the late 1950s. The cumulative mass, c tons, of all the satellites in orbit can be modeled as an exponential function of n, the number of years since 1960, by the equation c equals 120 times 1.12 to the exponent n. So c is the cumulative mass, and n is the number of years since 1960. So our first question says, determine the cumulative mass in 1969, the year when the first person walked on the moon. Now remember that n is the number of years since 1960. So in 1969, n would be 9. So that's what we're going to plug into our equation. C equals 120 times 1.12 to the exponent 9. And for a question like this, you would just type it into your calculator, and we find out it would be approximately 333 tons. Okay, now the next part of the question says, according to the model, when did the cumulative mass become 4,000 tons? So now we have a little bit more work to do. So in our equation then, C is 4,000. So we're going to replace C with 4,000. And then remember from the last lesson when you were learning to solve these types of equations, the first thing I told you to do was divide both sides by this number in front of the brackets if there is one. And this particular question should look familiar because it's actually the same equation I gave you in your lesson yesterday. So this reduces down now to 33.333 repeated. And on this side, 1.12 to the exponent n. So then we can rewrite that in logarithmic form and say n is the same as log 33.333 repeated. Sorry, I'm jumping ahead here, aren't I? Base 1.12. I didn't write that very clearly. Let me make that a little bigger. I was jumping ahead to the change of base formula there. So, make this a little clearer. N equals log 33.333 base 1.12. Then we can apply the change of base formula. So n equals log 33.333 divided by log 1.12. And that equals approximately 31. So 31 years after 1960 would be 1991. So therefore, the mass was 4,000 tons in 1991. Okay, next one. A school has an enrollment of 1,200 students. The population is expected to grow at a rate of 1.5% each year for 10 years. What's the growth factor, and when was the population 1,230? So in this question, we know that the growth rate is 1.5%, which as a decimal can be written as 0.015. So that means our growth factor, our B value, is 1 plus 0.015. So our growth factor is 1.015. So now in our equation, we're going to use the formula y equals ab to the x. We just figured out our b value, so 1.015. I'm sorry, I forgot my a value. The a value was given, 1,200. Now the growth factor is 1.015. And our exponent is x. Now the question says, when was the population 1,230? So we'll fill 1,230 in for our y value. And again, this is where prior to logarithms, you would have had to use trial and error to solve this kind of question. But now we can divide both sides by 1,200. Make this into a decimal, so 1.025 is equal to 1.015 to the exponent x. Rewrite this equation in logarithmic form. So x, my pen is deciding to quit here, x equals log base 1.015, and we're finding log of 1.025. So log 1.025 base 1.015. Use your change of base formula. So this would be the same as log 1.025 divided by log 1.015. So x is approximately 1.66. So therefore, the population was 1,230 after 1.66 years. Okay, next one. In 1995, Canada's population was 29.6 million and was growing at a rate of 1.24% per year. Calculate the doubling time. Now the doubling time is the length of time it would take for the population to double, just as it sounds. So let's think here. In our formula, y equals ab to the x. This is another exponential growth example. So our population initially was 29.6. In brackets, we'll write million, just so we remember that our answer, we need to use millions on both sides for both values, in other words. And our b value will be 1 plus the growth rate, so 1 plus 0.0124, because it said the growth rate was 1.24% per year. So our growth factor is 1.0124. And in this case, we're finding the time it takes for the population to double. So we're looking for when the population is double 29.6. So if we multiply that by 2, we're looking for how long it takes for the population to reach 59.2. And again, that would be million. Okay, so we fill these values into the formula. Okay, we'll begin solving by dividing both sides by 29.6, that number in front of the brackets, which of course leaves a 2 on the left-hand side, which makes sense because we're trying to find the length of time it takes for the population to double. So now we're going to rewrite this in logarithmic form. So x is equivalent to log 1.0124. I'm sorry, I've got that backwards. That is the base. Log 2, base 1.0124. Use the change of base formula. So x equals log 2 divided by log 1.0124. Type that into your calculator. So x is approximately 56.2. So therefore, that didn't come out very clearly, did it? Let's try that again. X is approximately 56.2. That's better. So therefore, the doubling time is 56.2 years. And we have one example left. It says after consuming caffeine, the amount of caffeine left in your system decreases at a rate of 13% per hour. Write an equation for P, the percent of caffeine left in your body after n hours. So because the percent of caffeine is decreasing, we know this is an example of exponential decay. So that means we're not going to have a growth factor, we're going to have a decay factor. And that decay factor, our B value, will be 1 minus our decay rate of 0.13. So our decay factor will be 0.87. And the other tricky thing about this one is we're dealing with percent. So the initial amount in a percent question would always be 100. And in brackets, we'll just put percent to remind you. So your equation then would be P equals 100 times 0.87 to the exponent n. Part B says if there's 88% of the caffeine consumed left in your body, when was it consumed? So now in this question, we're going to fill in 88 as our p-value. We're going to divide both sides by 100. So 0.88 equals 0.87 to the exponent n. Okay, by now you should know what to do next here. We need to rewrite this in logarithmic form. So n equals log 0.88 base 0.87. Use the change of base formula. So n is equal to log 0.88 divided by log 0.87. And with your calculator, evaluate that. And we find out that the caffeine was consumed almost an hour previously. So therefore, the caffeine was consumed 0.92 hours, in other words, not quite 1 hour, earlier. And that concludes this lesson.